Thank you for coming today. My name is Fernando Novoldi. I'm a security consultant for IOActive. And we're here today to talk about the highly exploitable behaviors in programming languages using differential fuzzing. So the idea behind this is that the majority of talks that we see normally at offensive security conferences is about bugs that have been fixed, have been solved, and they show you the outcome of what happened in the middle. I will try to do something similar to how I found certain things, but I will show you things that work. So the thing about bugs is that normally they need to be fixed when you're releasing them, but the thing about features is that you don't need to fix them because they're features. So I did a number of tests in 5 programming languages: JavaScript, Perl, PHP, Python, and Ruby. And I came across a series of things that were not documented and they were unusual. And I will share with you what I saw. To be able to find them, I wrote a type of fuzzer that helps you expose these behaviors. There was nothing when I started doing this. I wanted to find, specifically, I wanted to find things in JavaScript. But then I realized if I can do this for JavaScript, then I can do it for other programming languages. And if I can do it for other programming languages, I can make it for everything. So I can make a framework out of this. So I made a Python project that works in multiple operating systems. It gathers all the information. Whenever you're running a fuzzing session, you're executing things, so you're getting output from the standard output, the standard error, you're getting crashes, you're getting hangs, you're getting time, the information about time when you're executing something. You're getting network connection, you're getting a lot of things that are going on whenever you're executing a piece of software with a certain input. And the idea behind this is that you can expose the unexpected behaviors of those executions. I'm going to show you how. The final goal of what I did was to try to get more vulnerabilities from fuzzing sessions. When you're fuzzing something, there are a lot of possibilities that can come out of there. So this is what I tested. 5 programming languages, a lot of interpreters from those programming languages. What I did, I manually checked which were the functions. I tried to do my best job out of this. It may not be complete, but it was as complete as possible. So I got a lot of functions, and then I put up certain values between 5 and 30 values. The values being the capital letter A, the number 1, the null value, and so on. Nothing really crazy. So depending what do you do, if you're testing software, you may care about this because you may find other ways to test what you're doing. If you're a developer, you may care because you may affect, well, I didn't do that. If you're a developer, the thing is that you may affect, an attacker may affect the underlying programming language instead of the application. So when someone writes a piece of code, the attacker normally tries to affect the application, but if you affect the underlying programming languages that is processing the application, is broken nevertheless. And if you're a security consultant, you may care because you may try to exploit this, or you may try to fuzz things to get more issues. So we'll briefly show you what came out from my fuzzing sessions, from the differential fuzzing analysis that I did on the software, and eventually the things related to the programming languages findings, the external differential fuzzing. So when it comes to fuzzing, who has fuzzed in the past in here with any type of fuzzer? Cool, cool. So who has developed in here applications as well? Any type of programming languages? Okay, cool, thank you. So when we're fuzzing something, there are 2 big names that comes into people's mind. The first one being AFL, fantastic piece of software. I'm not getting even close to that. And Peach, great again, has a lot of features that you can use to expose vulnerabilities. The thing about these fuzzers is that merely they try to focus on how you're crashing the software. Those are the things that care about the main fuzzers nowadays. So the idea is that you're inputting massive amounts of unexpected data into the test target in an attempt to make it crash or eventually hang. So those crashes and those hangs are being saved, and they're being later analyzed to see if you're getting any vulnerability. Again, the concept is shared among all fuzzers. You're trying to do something. If you found a particular condition, you save it for later. So crashing a piece of software is not that hard. So as I was working with the fuzzer, I came across the thing that, well, this is not what I'm looking for, but I'm coming across all these crashes. So I found crashes in all the interpreters, mostly. This is an example for Ruby. This is what happens with the Facebook implementation for PHP. It crashes. This was the only one that I tried to report. And since they said it wasn't remotely exploitable because an attacker couldn't exploit that, this was not a vulnerability. So I stopped trying to report these crashes in PyPy, in Perl, and in Chakrakol, the Microsoft implementation of JavaScript. So you can crash whatever piece of software, right? Of course, you may not get a serious vulnerability out of a crash, but it's the starting point. So what's the thing with differential fuzzing? This is where things start to get more interesting. This is where I started this project because I wanted to gather certain pieces of information that I was not getting from any type of fuzzer. The idea behind a differential fuzzing process is that you're executing one or more similar implementations to compare the standard output and the standard error. That's how you're getting the issues in here. Instead of crashing the software, you're having a good execution. You don't want the software to crash. And you're checking what's the output. And if it differs in some way, then you're analyzing. You're analyzing different results from executions that should have the same values, ideally. So, of course, there is a long history on this topic. I'm not the first one doing this. The first one was in 19 years ago when they were checking for bugs in C compilers. Then 9 years ago, they checked that certain pieces of software could leak stuff through network connections. And that was awesome because you want to know if a piece of software is leaking something. That was great. The next one was in 2014 when they were trying to find bugs in SSL and TLS implementations. This one was the most interesting. This was to find bugs in JavaScript made by the people at Mozilla. This is the differential fuzzer that has been most developed so far to try to find issues in Firefox, and it works really good. And the final was presented on this year in Black Hat to try to find bugs in cryptographic APIs. So these implementations were focusing on a particular problem that they were trying to solve. They were trying to compare the results of the two C compilers that were made by different people, for example, and they were generating different things. So the idea is that you could do all these things, but with one piece of software. And the bugs that you're going to get from here, this is where it becomes interesting. You may have different implementations. Think, for example, when you have Python and you have PyPy. The same thing, but it is trying to execute things with different implementations. You may have different inputs. This happens for any piece of software. So suppose that you're trying to execute a program and you're reading a file. You're executing a program and you're reading something from the command line. The same piece of software may have different inputs and it may behave differently, and it does. You may try to fuzz different versions of the same product. You may find things that have been fixed or things that have been broken in different versions when it should behave the same, perhaps, or not, depending on what was changed. And finally, when the behavior changes because of the operating system. So the idea is that you're checking values, you're running the same thing, and it should give you the same output in the end, right? If it doesn't, then something's weird and you should analyze what's going on. So instead of it crashing here, we're trying to see what happens when you have a different output. So the first three examples are going to be based in JavaScript, just because it is easier to follow online. The last one will be related to Python. So for the first three examples, first we're going to talk about different implementations. Google does V8 to process JavaScript. SpiderMonkey was made by Mozilla. And finally, Node, which is running over there, if I'm not incorrect, the V8 parser. is trying to execute, all of them are trying to execute the same thing. They're trying to print on the console the value of the object this. So in here, we're getting that the value is the same for these two actors in here, but Node is behaving differently. Is it bad? I don't know. It is different. One of them is right. I don't know. We're talking here, same programming languages, different implementation. Now let's talk about one single implementation, Node, but using different inputs. So one implementation, different inputs, different results. On the left, you're trying to print the object this, and you're processing that by trying to call Node and the name of the file that you just written. The output is that empty dictionary. On the other hand, if you execute it on the command line, you get another result. So which one is real? Not so sure. I don't care very much about this. But I do know that this is not what I would expected at a minimum. And finally, same software, different versions with the same input. We're trying to execute the same thing, the object this. In a really early version of Node, nothing was being printed. Somewhere along the process of the development of Node, that changed. And it exposes the path, the current path, the home, the process ID, and so on. So same piece of software, different inputs, different implementations, different versions, things may change. And it gets a little more interesting when you're comparing different operating systems. I couldn't find this specifically with the JavaScript implementation, but I found it with Python. So I did fuzz all these software in all the programming languages, in all the operating systems, trying to find different things that were weird. And this is something that it is easier to see why it's different. So in Python, you have the CMP function that compares two objects. It is fairly straightforward. You put two things and it tells you if they're different or not. So the following one-liner tries to compare two floating point node and number values. Now, if you compare 1 and 1, the result of that should be 0 because it is a reflexive value. However, floating points have a non-reflexive particularity that they should not be 0. So probably the value should be 1 or -1. And when you execute this with different interpreters in different operating systems, you may find a common pattern of the value 1 being across them, except for Linux when you're using the main parser for Python. Why is that? It's odd, it's unusual. I don't know why it's happening, and I don't know how it may affect other pieces of software, but it's there. PyPy just doesn't care about this rule, so it does 0 for all of them. It shouldn't be. So, we talk about fuzzing. We talk about differential fuzzing. Now, what's the thing with the extended differential fuzzing? What else can we get out of this? So, since I was trying to fuzz programming languages, the thing about programming languages that is really, 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 really interesting is that there are a lot of things that may happen on a programming languages. You can read a file, write it, open a network connection. All the things that an application does are embedded on a programming language. So if you're able to truly fuse a programming language, you should be able to get all the things from an application when you're trying to do that. So you want to detect more things, not just the different things with the standard output, not just crashes. You want to try to get when code is being evaluated, for example, for a programming language, when something is being executed. Moreover, you want to know when something from the operating system gets executed. How do you know when you're executing a piece of software if something else is not being executed on the operating system level? You want to know when the network connections are being opened. You want to try to trap that and take a look to see if was it expected. We want to know when files are being read. Can an attacker trying to read a file that was not supposed to? Can the attacker do that? And eventually you can try to get some meta information, for example, the time required for the execution, and analyze if perhaps there was not a hang, but there was something unusual about that one. And on this area, you can find other things that you may care about. So traditional fuzzing only checks, as I said before, the crashes and the hangs. Differential fuzzing will focus on the difference between the standard output, the standard error, or eventually if something is being leaked. The fuzzer that I made tries to find all the areas that were available for applications. I'm trying to execute it one time, get as much information as possible, and then analyze the information. So this is where it gets funny. I knew this worked because I tested in the past manually, and I knew the programming languages were going to show some of this. I didn't know what I was going to get. Let's start with Python. In Python, everything looks really, really good. In fact, I'm just showing this to show you something about Python. These are only undocumented things that I came across. The first one is MineTools has a function pipe2 that the value ID will get executed with whatever you put over there. So normally when you look on the Python library, which are the functions that execute code, this is not over there, but this is a possibility. If you're able to affect this function, you may be able to execute operating system commands without using the operating system library. The same thing goes with type picture, where you put, for example, an ID over there and will get executed. You will see it over here, not a big deal. What I found it to be interesting and funny, I think this is what it gets a little bit more weird. If you're talking about the same library, I don't know if it was the same library. When executing the pager function from PyDoc, if you set the environment variable pager, it will try to execute whatever it contains over here and will write it on the standard output. I would like to know that if this is going to happen on an application, if you have it over there, you can take a look and see if something is vulnerable. So let's move to Perl now. This was really funny. Perl had the only programming language that was able to parse a piece of code where it was not expecting to be executed. You can see it in the middle of the stack trace of the embeddable time map that I have no idea why they decided to execute code, but it did, and that's bad. At least you want to know it doesn't say anything on the documentation about this. So again, these are all features that are over there. You can execute this right away. Let's talk about JavaScript. Again, in here, you're trying to use the function require when what it does is it tries to read a JavaScript file. On the left, you have checker code that says, the first thing that I came across is an invalid character. I cannot read this. This is not a JavaScript file, which makes a lot of sense. On the right, I'll show you the first line and say, hey, this is not JavaScript. If it is not, don't show me this. So, JRuby, funny. So, what I did was compare Ruby to JRuby. And again, I put all the functions, I put all the values. I recently learned that there are two JRuby different versions, forks. One is the version 1, the other one is the version 9. They differ how they do things. Both are the latest versions. The line of V1 behaves in one way and the other one behaves in another way. So in here, break files are something related to Ruby that execute Ruby code, which is cool. It's okay. You have a load break file method that it reads Ruby code locally and execute things. So when you're trying to do something on the left with Ruby, it says, well, that file, the remote file that you're trying to load doesn't exist. It's not local. However, JRuby doesn't care, opens a network connection, retrieves the Ruby code, and gets executed. Magic. Now, PHP. This is something, I'll save it for the end because it's a little bit more complex and it's a little bit more funny because look what happens in here. On the left, you have a string getting executed by shell exec. PHP has like 4 different ways of execute operating system. This is one of them, shell exec. This thing that I'm going to talk about works for, I think, at least for all the functions that execute operating system commands from PHP. On the left, everything is clear. This is not a bug, this is cool, this is expected, you're executing things, things work as expected. On the right, however, you're trying to execute a constant, the constant ID. And PHP, when it tries to execute this one-liner, it only has this. It only has this information. I'm trying to execute the constant ID. PHP says, ID is not here. So what I'm going to do, I'm going to assume that ID is a string, and I'm going to execute it. Well, I would prefer if you didn't do that, because something like this may happen. Let's suppose that you have an application that has two files. The first one defines the bash constant. This is going to execute the command man, okay? The second file is going to execute the constant bash, is going to put as a parameter what we send it on the page parameter, and it's going to show it. Let's see if a live demo works. First of all, I'm going to clear the logs. So here we have the index PHP that I was telling you about. At the top, you can see that I'm using the page parameter. I'm putting ls over there. I'm trying to see the man page for ls. So if we change the ls to something else, we will... Okay. Better? No? Okay. You can see it over there. I increased the font, I'm sorry. I don't know where it is, to be honest. Where? No, the control plus, or perhaps. Oh, there, with shift. Better? Okay. So we have the man page on top. We have the logs over here that are clean right now. Let's do a refresh in here. We will see the getting here, just something normal, as expected. But what happens if we call directly the functions page? So right now, if I do this, the constant bash is not going to be executed, but the string bash, and you can do whatever you want, right? Because bash is getting executed. There you have the etc password. And here, PHP assumed bash just because it was not over there. So it decides that it's going to execute the string instead of the constant. So if there is any application with PHP defined in this way right now, you may get code execution depending on the name of the content. Depending how the constant has been named, you may get something like this. So this is where this was kind of safe, and this was in case the demo failed. We have a bigger font here at a minimum, and this is how it looks like when you're executing code, when you're calling the functions PHP directly. So this is all due to the thing that these constants will be treated as strings if they're not found. So the final idea behind all of this is that hidden applications in programming languages can affect the security of applications. Even though you're not hacking the application and you're hacking the underlying programming language, you may still be able to attack the application. Doesn't matter how secure it is. The extent of differential fuzzing can expose hidden behaviors in different types of software. And the thing about this is that if you're able to fuzz a piece of software on different operating systems, for example, or in different implementations, Are you getting different crashes all over the place, but you're getting similar crashes on different operating systems? Perhaps the new vulnerabilities will try to attack multiple attack vectors at the same time by focusing on the vulnerabilities that are shared amongst the majority of implementations or operating systems. If you want, you can, the fuzzer, it is available right now. You can download it from here. If you have any problems, I will continue developing the fuzzer, fixing bugs or stuff like that. And if you have any doubts, we have a few minutes to answer a few questions. If not, you will find me outside for the next half an hour. Anyone wants to ask something? Sorry.
Thank you. Great presentation, by the way. Just curious, do you have somewhere hosted where we can actually find all of these snippets, code examples, and where you document all of these findings? Because this is perhaps a small sample. Where is the actual everything?
Along with the Black Hat Wood release, the white paper associated to the white paper contains all the snippets of code and contains all the theory behind this tool, and it is all disclosed over there.
Okay.
It will be released.
Thank you.
Any other question? Thank you very much.